Right, good afternoon, ladies and gentlemen. Here's a little talk on optimizing an application. This is really a study in tools and looking at a small real-world application and seeing how you can use some tools, and I'm using Linux to do this one, to guide this process of trying to find out how to go faster. So, first thing, this was an application that was, I wrote for a client in a bit of a hurry, so please don't necessarily look at my coding style. This was done under a certain amount of time pressure. I want to show different versions of this one. I've got 9 or 10 different versions going through, saying, what do I do? How do I work out what to look at next? Here you'll find some dead ends. There's some things I tried. I went, oh, I thought that's definitely going to make it go faster, and then it doesn't. 1 or 2 moments of, oh, you idiot, and a few other bits and pieces. I want to show use of tools, so things like valgrind, particularly the cachegrind tool, and compiler explorer, perf, strace, a few other things like that. How to use these tools, how to interpret their output, and how I use bits of the C++ library. So it's a relatively standard, straightforward piece of code. There's nothing here. There's about 150, 200 lines for the whole thing, plus a large amount of the JSON library. Okay, what was the problem? So this was a client who'd got an IBM mainframe, and they had some interesting fun with this. And they were in a potentially a disaster recovery scenario where they've got a lot of data they needed to recover. Those of you who are somewhat younger than me may not realize that there are machines in the world that do not use ASCII. They do not actually store the characters that you're used to, A to Z. They actually use this thing called EBSTIC, which is Extended Binary Coded Decimal Indicator Code. So that's BCD in the middle, you'll notice there. So that's a bit of a giveaway. It's actually BCD. They use a lot of stuff for arithmetic. What does that look like? So first of all, what's part of the problem space is having a look at this. So this is a nice piece of IBM stuff here from way back when, and let's have a look. So this is the code page for this one. So these are hexadecimal across the top, first digit and second digit like this. Okay, lots of weird symbols and other stuff going on and weirder things like this. But the thing to notice is we go here. Okay, A, B, C, D, E, F, G, H, I, O. J, K, L, M, N, O, P, Q, R, divide. What's that doing in the middle of the alphabet? S. S doesn't even start. And when the you go, okay, you've now set me a precedent here, but I've got one of those things there. What's that doing there? That should be an S, but it isn't. It's down here because for some reason maybe they shifted. I don't know why they did this one here, but at least the digits are actually in the right place. So this was the part of the problem domain, which was I'm being given stuff in that format, and I need to translate it. So that was part of what I was doing. And what they gave me were some files which are COBOL copybooks. These are binary files. And I went, well, what is that? I have no idea. Better go and find out. I need to convert them into pipe-separated ASCII. So let's have a look at what that would look like. So let's have a look. So let's have a look at something like this, this one here. No, that wasn't what I wanted. I wanted this one here. So this is, so please don't leave the room. This is COBOL. Yes, it's all in uppercase and it's got dots on the end of everything. That's actually just a struct in disguise. And the way that COBOL lays out its data is just fixed. It's fixed size binary. It's just lumps of stuff like this. And these are actually just unions. So they're discriminated unions with a tag usually. It says, well, I've got this one here. It could be this record type or this record type. So there's usually a record type and some other things. So these are basically kind of layout. It's fixed format. So this says this is X10. So this one here is a trading number is 10. This is a filler of 2 spaces, and they're in alphabetical. I've got some other ones which are computational values. So those are integers. I've also got some decimal values in here. So I've got pics and decimals. So basically I've got integers and strings and binary coded decimals. Right, okay, what I wanted to do was to, so that was the input, sorry, I got the wrong one, that's the output format. So basically what they wanted me to do was to produce something that had all these fields in it. Yes, they actually had commas on the front of the names, which really, when you're doing this one, you immediately think you've gotten off by one area when you see that in the name somewhere. No, that was the names they gave me. That was kind of fun. So that's what I was trying to translate, that first one, into this second one. Let's have a look at the XD. Let's have a look at 400 bytes of this, and let's look at some file like this guy. So here is the first 400 bytes of the file. Right, so you can probably see there's a lot of 4040s here, and those of you paying attention will have actually found that that's a space, and it's like, oh, I need to try and decode this one. So first of all, I've got to try and work out what the heck this damn stuff is, and then if you've ever done this kind of stuff, you're sitting here with the translation table and going backwards and forwards, doing the hexadecimal. And this took me a while to work out. That's not part of this story, really, until you find out there's this magic setting which goes, thank you very much. So I know when I discovered that XXD had got a please show me EBCDIC format, life becomes an awful lot easier because you can now actually see the data in something you can recognize. So that was a damn good start. Anyway, so that's basically what was going on. You can probably see something here. It goes, right, MK, blah, 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 MK12 like that. So you can probably work out from this that this one here is about 20, so it's 16 on line F48, 248. It's about a 54 byte fixed length. So it's basically 54 bytes of chunked stuff. So you can see MK12, 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 etc. So it's basically a fixed file, a binary format. So you might think, well, actually, look, this looks not too dissimilar from something like binary that you might get down in a hex packet on a network. So actually, it's not that different. Anyway, that was part of that. Oh, I didn't show the output, did I? So they gave me some examples. So I wanted to see what the output looked like. So ASCII for one of those ones here is like this one. It says the output that they wanted was this. And so that's a header row, and it's all pipe separated. If I show the other one, that's probably the one that doesn't match up with the other one. But basically, you can see all those figures there. If I took I think I got the wrong one, didn't I? That was, which one did I do before? That was 12, right. See if you can take the 12 and actually look at the right one. So that's the translated version of that binary, which is all those things, MK12, blah, 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 pipe separated, and all of these strings, which are normally fixed size, are all truncated, and there are some empty ones, etc. And this was, now, they were taking these off their IBM mainframe, and they were trying to stick them into their data warehouse. And as I said, this is a disaster recovery situation. So time is kind of important because they potentially don't have the mainframe around. So how do you do this one? So you need something else to do it. They started off and they gave me these three, and I said, oh, I can hack something together and quickly hack something for those three. And they went, yeah, we've got another 100 or so different formats. We need something generic. So that was a bit of a laugh. They've got hundreds of gigabytes of data translate as well. It's like, okay, how are we going to do this one? How are we going to create a configurable conversion tool? So I worked out, well, actually, what I really wanted to be able to do is to have something that looked a little bit like this. And I went, well, maybe you can specify this kind of. So I said, let's create a JSON structure that said, right, record length, 87 bytes for that particular thing, printing header rows, separators, etc. And then I basically had offset and length and type with a name for all those ones. A fairly straightforward structure. I'm sure that you would have come up with something very similar yourselves, whether it was JSON or whatever. It just carries on going for lots and lots of different things. So that's kind of what I decided to do at that point. The client had looked around on the internet, and they'd found an open source C# tool that was configurable, had XML, lots of other things, and they tried this one. It was actually horribly slow. So they took a 2 megabyte file, and it took about 11 hours to process, and I thought that really wasn't very good in terms of throughput. So they had a word with me, and we thought, well, let's see if we can try some C++ for that. So that was basically the problem. Okay, so before we get into that, I wanted to talk about performance, how I look at performance, and what I call a performance story. So you start off with something that's too slow. So what you do, you start timing, you start looking at, you start measuring. Measuring is very important. Guesswork, as you will see later on, guesswork doesn't always work. There's some informed choices, but this is basically the steps I almost always go through for this one. Right, first of all, stop doing stupid things. Unnecessary calls, get rid of I/O, get rid of network, get rid of silly things that you're doing and formatting things in odd ways or whatever. There's usually something a little bit not right that you're doing your first one, and it becomes quite obvious. There's something obvious that's obviously wrong. So first of all, get rid of that. There's no point in trying to do cache-aware things like this if you've got some great rocks in the middle of it. So first of all, do that one. You know, you're going around a loop and you're calling something in the loop. Just take it out the loop if it's loop invariant. Next thing, I usually find that it's something to do with memory after this. It's going to be malloc or memcopy or memcomp. So it's those memory things which are usually the next on a list. In this particular case, it isn't, but for most things, it is there. So you need to get rid of memory allocation, sort of that out, getting temporaries out of the way, and copying of data, move semantics, whatever you choose to do. How do you stop allocating lots of stuff, doing pushbacks on vectors and pops and whatever, or strings? Strings are a big thing. So for performance. So that's the next thing I would then look at. Once I've got that, I go, well, maybe now I can start looking at algorithms. Maybe I can get an order n algorithm down to order log n or on 1. So usually it's this point that you start to get some interesting changes in your application. At that point, once you also, and this then also depends on your operational profile. What do I mean by that? Operational profile meaning the distribution of requests. Is it heavily read-biased? Is it read-write? Are there certain operations which happen much more than other ones? What do you know about the domain? What do you know about the types of things that you have? That will come in useful later. At the bottom, and only at this point, is it worth then really starting to think about memory bandwidth issues and taking extra advantage of caches, the way you lay out the data, etc. Yes, some of these can move around, but typically I find it tends to be this kind of story. And you start at the top and you keep going until it's fast enough. So for some things, fast enough may be good enough. You just go, well, once I'm here, I'm right. I'll just get rid of the stupid things. So don't spend all your time doing this one, but me being utterly obsessed by performance, I'm down here anyway, so we're going to end up down here. Here is a nice little picture from, I borrowed this from Sergei Ignanchenko, which is operations, different types of operations on CPUs and other things. And notice this is a logarithmic scale, so this is orders of magnitude. So this is quite a lot over here. This is in the millions. And you start at the top and you go, right, simple register add is less than 1 cycle. So you can do multiple ones in that. Modern machines are great. They can do lots of things in parallel, and we'll see some numbers for how many instructions per cycle we've got in a moment. Memory writes, because of store buffer, you can write those on back. It obviously depends on your architecture. Right branch of if compared to wrong branch of if. So 1 or 2 cycles if you predict the branch correctly, about 10 to 20 cycles if you don't. So there's an order of magnitude difference on your branch predictor. We're going to look at cachegrind, we're going to look at where you got that right and where you've got that wrong based upon your data and your code. So we can actually simulate that. Floating point addition, multiplication, reasonably fast. They're actually faster than accessing from L1 cache. 3-4 cycles, it may be less than that. It depends. All of these things depend on your architecture. You need to measure them and find out. L2 cache out here, about the same as a branch prediction miss. Floating point division, this is quite slow. It's actually about the same as square root, which is kind of interesting. And you're going, well, okay, so actually calculating the square root is potentially faster than calling a function. So this is a direct call with C, around about the same as division, an indirect call through a pointer, a virtual function call even worse than that because you've then got this pointer as well to do that one. So you can see that we're getting into some slightly slower territory, around about L3 maybe. If we go all the way out to main memory, 100 plus, etc., this depends if it's on the same socket and other things. So 200 cycles or so all the way out there if you've got a cache miss. Compare 200 cycles of this as opposed to maybe a couple of cycles there. 2 orders of magnitude. Every cache stage that you go is probably a factor of 4 or 5. Right, now we start getting into some considerably slower things. Allocation and deallocation, malloc. That's always a good one for slowing you down. So we do that one. Why is this one here? Remember that malloc really is a question of saying, please go and get me some memory that's not in use. This translates almost exactly to, please get me memory that's not in the cache. Please go and get me memory that's really slow because I'm now going to be doing this all the time. So allocations, although that's the direct cost, the indirect cost can be considerably higher. You're jumping off into bits of RAM that you haven't seen for a while. Kernel calls, 1,000 cycles or so. So one of the things obviously we want to do if we want to go fast is avoid system calls. So we'll look at some of that as well. Thread context switches. By the time you made a system call, gone into the scheduler, worked out what to do, and then come back out again, there's an overhead to that. Well, actually, the cost of a context switch is even more than that, because really it's out here, because what happens with a context switch is that you completely trash your cache, because you suddenly go somewhere else and you go, oh, where's all my stuff gone? You spend all your time trying to get stuff back into the cache, and then somebody switches you back out again. The particular application we'll look at is single-threaded, so this isn't an issue here. Also, I'm not using exceptions, so I reference Herb's talk this morning about exceptions and the cost thereof. Interesting point. People think, yeah, we're going to do multi-threaded, that's great. Well, good threading, if you get perfect linear speed-up, scalability, you might go 1 order of magnitude that way. 8 cores, roughly an order of magnitude. So you might go 1 order that way, if you get it absolutely right. Typically what will happen is you'll get it absolutely wrong, and you'll go 1 or 2 the other way. And my general theory is add cores go slower unless you know what you're doing. So be very careful about doing lots of stuff like that. Anyway, so that's just some of the things. We want to avoid these bits, because obviously these are several orders of magnitude slower than that, and disk access is somewhere off in the next room. So we obviously want to avoid that, because guess what? With 2 gigabytes of data to process, I'm going to be showing you 200 megabytes rather than 2 gigs, but still that's a not inconsiderable size. What am I going to use? Well, there are plenty of tools out there. So on Linux, there's perf, and I'm going to show you a number of things. We're going to do perf, perf stat, perf record, and perf report. Some of those ones. There's older ones like oprofile, which is a sort of kind of a bigger roll up. You can use top. First of all, can you find out whether actually, top, htop, is your application CPU limited? Because if it's not CPU limited, then you kind of need to make sure that that these techniques here, you really want to get rid of all the I/O before you start tweaking with the CPU, because that's not going to, you need to tackle the bottleneck. Which is why you want to bring in something like I/O top. It says, what am I doing here? Am I actually doing I/O? Then you can start deciding whether you do the I/O, somebody else does it. Classic things like VM stat, I/O stat, which is where's this going, how many context switches have I got, how many interrupts, and all those other kind of things. So these are generalized system tools you can use to see what's going on, to give you an idea where to look. They don't tell you in quite that level of precision, but we'll see some other ones. I'm going to be using bash time because in the end, people care how fast does it go. How do you measure how fast? Well, how long did it take? Wall clock time is pretty good. The nice thing is they're full speed. You don't have to compile anything in. You don't have to do anything else. They're often sampling based, but things like bash time will just give you that. There are commercial tools as well, and I'm sure some of our sponsors would love to talk to you about some of this. You can modify your application. You can start compiling it with gcov, gprof, and other things like that to try and see what's inside. I'm not going to do that today, but that's another option. You can use high-resolution clock for timing bits of code. Where is this one here? Boost has a CPU timer. I'm going to spend a little bit more time today on things like the simulators, valgrind. The valgrind tools. So callgrind, cachegrind, there's annoying differences between the two. We'll talk about that in a moment. They're slow, so they can be several orders of magnitude slower, but they give you very, very good insight as to what's going on memory usage. Right, so here are the command lines for what we're going to do with. So C++ 11, which version? My favorite is 03 and March native. If 03 breaks your code, that's because your code is broken. You've just found out it's broken. Whereas an 02 is, well, some people think it's safer. I prefer 03. March equals native. Now, what does that do? So that's -m, architecture equals native. That says, compile this for the current machine. If you don't put something like that on, what will happen is that GCC, which I'm using, or Clang or whatever, go, yeah, I'll just compile this for some sort of kind of general machine, and it doesn't use all the instructions on your machine. You've got this lovely hardware you've just spent all that money for, and you don't use the instructions because you haven't told it it can. So it takes a conservative approach and says, well, maybe it's an i686 from about 10 years ago. I'll try using that. Maybe we've got some SSE or some MX. We'll just drop some of that in, maybe. But if you say March equals native, you go, oh, look, I've got all these lovely instructions. I'll use them. So that's what I'm going to do. -G, because I want to get the debugging information in there, just so that we can see what's happening, and then we'll run this one. So I can run valgrind, see the memory allocations. For this particular case, I'm not chasing memory allocations because I've basically got a fixed size buffer, and then I'm just processing this with a big lookup table. So I don't need to worry about memory allocation on this one. Valgrind, so the cachegrind tools on callgrind, they are valgrind tool, cachegrind or callgrind. They are similar, but not quite the same. And they have annoying differences in the command line. So, branch simulator, please show me the branches. So remember all the predictions about whether you get it right or wrong. That's a factor of an order of magnitude in difference in speed if you get prediction right or wrong. And simulate the cache, please. And we'll see some details here. We'll run some stuff. When you run it, produce an output file like this, and then you run your application, do whatever. That will produce this output file. You then have to post-process this using an annotation thing like this. And you can say, right, OK, run that one here, and then show me on a line-by-line basis what's happening in this source file. You can also say auto equals yes, like this, and that says, go and show me all the files. So you can then start going into the standard library. OK, I'm using map or whatever, or vector. Maybe I'll go down there. We'll show you what you're doing inside string. It gives you really good vision on a line-by-line basis. Callgrind, very similar. It has some extra columns at the end, which give you some information, but it's very hard to interpret on the amount of, if you've read data, how much of the data have you actually read? So read amplification, if you know what that is. It will tell you, oh, you read an entire cache line, but actually only used 4 bytes on average. So that's a waste of a memory bandwidth. Slight annoying things about difference here is that callgrind annotate and CG annotate. CG annotate requires an absolute path name, whereas this one wants a relative path name. They're written by different authors. And the grep here is because callgrind annotate on the version I'm using spits out some stuff about use of uninitialized variable. I just want to get rid of that stuff, so it's just some noise. I'm going to be using the cachegrind one instead. So let's go and have a play. How do you think we're going to do this? Have you got an idea in your brain? How would you actually write this program yourself? What would you do, given I've got all these weirdo things going on here with stuff, and I need to do translation of this one here, and they're not next to each other, and loads of if statements and other things? OK, right. Well, the obvious way, anybody who's played this at all, is a lookup table, yes? So no prizes for looking at, for guessing that I'm going to be using a lookup table here. So first thing I do is fill it up with question marks going, well, if I don't recognize this one, I'll print a question mark. And I've got, so I basically special cased all the symbols that I actually need. And then I've got, right, OK, well, that's A. These are the ones from J. These ones from S, and the capitals and the ones. So I just filled up the lookup table. It's nothing particularly exciting there. What am I doing here? So this is the main. As you can see, the thing is 155 lines. It's nothing particularly exciting. So there's enough interest in here, and it's small enough to be able to use and understand. So command line arguments. So I've also got I've got the input file and the configuration file. For this particular one, I'm printing to the output. I will later on change that. But so I create a translator. I read this configuration, that big JSON file. I'm using the Lohmann's JSON thing, which is 17,000 lines. Which is why it takes quite a long time to compile my 155 lines plus 17,000 of his. So I've done quite well in code reuse. Print the header row, which is for the output. If you remember, I had the output pipe separated, and then I just go and process the file. Right, what's that going to do? Well, reading configuration. This is really nice, actually. You go, here's my JSON. I'll just read it, and I'll take in all those values, and then I'll pull out the things that I want out of here, and then go and get the name, the offset, length, blah, 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 and just loop through all that array. So I've basically filled up, taken the JSON, filled it up, done. Printing header row, I'm sure you can work that bit out. Process, right, okay, so I've got a record length here. When I first did this, I went, oh, that's record length, that's great. And I suddenly realized I'd use a GCC-specific extension here because that's not a compile time constant. Whoops. We fixed that later on. Anyway, so I read that thing in here, right, and then I go through all the fields, and I look at the type. So go through all the fields like this, and so if I think it's supposed to be a string field, then go and get the string and print it out. If it's an int, do this decimal. Nothing too complicated there. Get a hold of a string like this. So what am I going to do here is I'm going to go through, right, okay, you've told me it's this many bytes. I'm going to go back from the end and go, well, whilst it's a null or a space, come backwards. And then, so find the end, because I need to trim it. And then I'm going to run this thing through the translation loop. So I'll just translate the characters and then return the string. Okay, that's fair enough. Integers, that's pretty straightforward. I know how many bytes it is. Reverse. Now, why reverse that? Well, because IBM is big endian. Intel is little endian. They store the integer the other way around. So I need to reverse all the bytes before I can then say, oh, all right, now I can treat it like an integer on my machine and use printf and spit that out. Okay, straightforward so far. I won't go into this level of detail on the other 9 versions you'll be pleased to hear. Get the decimal, right, okay, so I need to go through this one here, and that decimal, is done a nibble at a time, so it stores 2 digits in every byte. So if it's 1, 2, 3, 4, it'll be actually hex 1, 2, 3, and 4 as 2 bytes. And then the next nibble at the end is either C or D. That's the sign bit. Now, why C or D? Those of you who have come from an accounting background might recognize that as credit and debit. Guess what IBM do? They do some things that usually deal with money on mainframes. So C and D are actually credit and debit, which is the sign bit, which explains why I've got this D here for the minus. Yeah, who knew? Well, I found out, didn't I? So having picked all that lot up, I then just sort of kind of shift it by the number of places I'm expecting, because I need to pick the whole thing up and do the number of places, and then just print it out. Okay, so this one has got so I've got translation table in and some other stuff, and here's the data I've read there, and a vector of fields, blah, 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 and something printed out when I did that one. Right, enough of that. Right, so let's compile this thing. And I'm going to run it on a smaller version to start off with. As I said, it takes a little while to run here. Okay, so we want to do... no, I don't want that one. Time a.out, and it's... what did I just have here? Which directory am I in? Rather than getting you have it all this lot, let me just grab this then. This one takes an output file like that. Let me run it on the whole thing anyway. So this will take probably 10, 12 seconds. So this is... So running my a.out, the JSON file, which is the thing that says all the things. Here's the input file, which is the big binary file, and I'm putting it out to that text file onto temporary. I'm running on so my laptop here is a Core i5, and it's got it's a solid state drive, so that's fine. If we go and have a look at that, So they did give me some test files. So when I did this one, we can actually go through and go, oops, there we go. So it actually produced the output that was required, and I could then diff that against the ones I did. So I actually had some tests, so I wasn't just running randomly data through this and going, yeah, I think that's right. So actually, I was doing a whole test on that. Okay, that's slightly larger than we wanted. So that's fine. Let's do this one here for something slightly smaller then. PIT. The reason I want to make this smaller is because I'm about to, if I'm going to run this under valgrind, I don't want to, it would take quite a while to do that. So, valgrind minus tool equals cachegrind, etc. So I could type the entire thing if you want. Please excuse me whilst I, so you don't want to see me typing all that, do you? And so I can take that there. So let's run a smaller one of this here. So what's that doing? So this is running the valgrind the cachegrind tool. So this says, so run cachegrind here, simulate all the branches, please. Give me the cache simulator. Here's my output file, cg.out, and then my command as it is. So what does this look like? What does this give us? So the first thing we see is, yeah, that was the command I ran. That's okay, I'm cool with that. L3 cache found, using its data for the simulation. This is a simulator. It has to decide how big the caches are, and it said, ooh, you've got an L3 cache in your machine. I'm going to use that for my simulation. And it calls it an LL simulation because it simulates L1 and the last level cache, LL. There's no L2 in the middle, it's just L1 and L3. 85 million instructions. Instruction misses, not very many, which is really rather good. So the cache miss rate for instructions is pretty much 0. That's good. Instruction cache misses are very, very bad. Well, if you think about it, you go, oh, I have this wonderful CPU and it has no idea what to do. And it just stops. It's just like, yeah, and, oh, thanks, you've given me something to do now. So cache misses in instructions, really bad. So fortunately, we don't do this one here. This one has a very tight loop in it, so it's fine. Right, okay. This is a summary, and it's not necessarily the easiest to understand this one, but it just gives you a general idea. Well, I got the miss rate, it's pretty low for here, for the D1. So what's this? D1 and LI1. So the L1 cache is split into an instruction cache and a data cache. So this is telling you about the I1 instruction cache and all the way LL instruction cache, or instructions. So this is saying D1 misses and all the way out to there. And actually you can see it really isn't missing much at all. It's quite a small file in comparison. It's 200 megabytes was not this one, but the one that took 11 seconds was 200 megabytes, by the way. So here we go, misses and read and write. We're going to see more detail in a moment when we've done this one. So that's that, and you go, yeah, okay, fine. Misprediction rate on branches, 2.6%. Well, not so bad. CG, annotate. Annotate and cg.out, like that, and I can say, right, okay, pwd, version 1 main. And there we go. So if I may not be able to see the bottom quite so easily, but we don't need to see the bottom just for a moment. Remind me to go back again. This is the output from CG annotate. I1 cache, 32 kilobytes, and a 64-byte line size. D1 cache, 32. The LL cache, the last level cache here, 3 megabytes. That's what it told me it was going to do. So there we go. There's my file here and the data file. All right, what's all this stuff? Events recorded. What is it recording? So it's recording the following things. And these are mnemonics for particular types of stuff. It's sorted in this order, and some thresholds can be applied. Here's a summary, and it's these things. Let's go through this one here. So this says, instructions read, 85 million. Instruction 1 miss, so 3,000. So this is basically the detailed version of what we saw, or that summary we had here. And this instruction cache miss there. Right, okay. I went to the data cache 25 million times. 16,000 times I missed the D1 cache. This is really very tight in cache, this one here. And of those ones, 8,000 went all the way and missed the main cache. This is all the way out to main memory. This is the, I need to do 200 cycles to go and get this one. This is the 30, 40 cycles, out to L3, and this is the couple of cycles to L1. So we're doing well here. That's for data read, reading from the cache. Data write. So we split read and write here. So I'm writing this one here, 13 million there. D1, miss. Why am I missing the cache when I'm writing? It's like kind of, aren't I writing? How can I have a cache miss? Well, the reason you have a cache miss is because actually a write into the cache is a read, modify, write, because you go, if I'm trying to write that byte over here, I actually have to bring the entire line into the cache, write it, and then send it back out again. So if that line's not in the cache, it's a miss on the cache to do the write. It's doing well here. Right, okay. Branch, conditional branch, if statements, basically. Lots of them. 11 million of those. Branch, condition, miss, 0.3 million. So 11 million of those, 0.3 misses, and that's where I got 2.6% up there. BIM here. This is branch indirect. So this is call through a pointer, or virtual function calls. That's this one here, and how many misses do I get? Because those are done differently, because the simulator goes like, where am I going to jump? If you have a lot of virtual function calls, for instance, and you're just jumping around all over memory, this goes up very high. Okay, that gives you a summary. What's the next thing you have here? So what you get here is basically some profiling. And this says, right, okay, so this is now on this is sorted on the left-hand side. That's what this thing here says. Right, okay, sort order. So it's sorting basically on the columns left to right. 14 million instructions in fwrite. Oh, okay. So this thing seems to spend most of its time writing. Okay, that's pretty good. So basic O stream stuff going on here. And when they're coming down here, excess put n. This is the stream buff underneath the output for the streams. Oh, look, now here's my code. Actually, I'm into my code now, and the rest of this one here now says process sentry. These things, by the way, that say sentry, like this, we'll see these ones again in a moment. These are the things on the I/O stream. So this is stuff to do with the I/O stream. Printf, memcomp. You'll always find memcomp or memcopy in here somewhere. Oh, there's another memory comp, and string length, etc. But these are down in the starting to get into the smaller stuff. Anyway, so that gives you this summary. Then the magic starts. Here is per line information. So I can now go and see, right, actually what happened here on this one here. So we were looking for things in the million. So, oh, here we go. We've got lots of stuff going on here. So where's this one here? Right, while begin. Here's my translate loop. Here's where I'm spending my time. And I'm going, right, okay, look, here I'm going 1.1 or 1.2 million data reads, 2 misses. I think that one's doing quite well here. This one, so that was reads misses all the way out, didn't go. Here's lots of writes into that cache because I'm writing back result, and I didn't miss it at all because guess what? Result is there. That's fine. So here we go. This is 400,000 conditions here and 94,000 wrong, which is the loop. So we get an idea here of 400,000, about 100,000. So this loop probably went around about 4 times. So I can tell reasonably quickly by looking at this one that this loop here is 4 times. So actually, it's probably because I'm in string, my strings are probably 4 long. So you can look at these numbers and go, oh, okay, fine, right. What else have we got here? Get ints. Oh, apparently on this file there were no integers at all. That's entirely possible. This is a short file. There are in the other ones. Now let's look at the decimal one. Okay, actually, you haven't got many decimals here in this particular one. So, well, that's fine. But this is the accumulator here, and again, you can see there's not many cache misses going on here. How long were these things? 16, 3 and a bit like that. So they're about 5 bytes long, which is probably about 5 times around that, which is probably about right. Anyway, that tells me my program, and you probably find that that's not exciting. Right, okay. What can be a little bit more exciting, though? Auto equals yes. Now, if we do this, what do we get? We get the same thing, but now we get it for the library. So there's my code. And now show me anything you think is of any significance. You can go and trim it if you want with some of those thresholds. And now it's going to go, oh, look, you're in the new allocator. Here's 200,000 there. Oh, look, we got 200,000 cycles here in the destructor. That's interesting. So we can go and find out, and we can filter, where is it spending its time in the library? Basic string, I'm sure we're going to be doing something in basic string here somewhere. So we're looking for things in the million. All right, okay, million. There we go. A lot of string length. So a million things are string length, because maybe it's about 14 million in write. Some other ones here, picking up the data, etc. Some testing of whether it's local. So basically, this is the small string optimization checks, etc. So we could go through this, but you get a really good idea and write down X-ray vision into your application. Here's where it's spending its time. Obviously, you're not going to go and change the standard library, but it's really useful to be able to get that kind of X-ray vision into that. Right, let's try something else then. So having run this on this larger piece like this, what I'm now going to do is to run perf stat. Actually, no, let's do that. Let's get a high-level view of what's going on. So strace minus C. So if you run strace and you see loads of stuff going backwards and forwards, you spend a lot of time looking at strace and going, what's going on? And it's actually just this minus C option is only a couple of years old, and it is very useful because it does this. Here you go. Here are all the system calls, how many there are, and how long they took. Thank you very much. That saves me an awful lot of time, because immediately I can go, right, 72% of the system calls were writes. And there's about 50,000 writes there. If I show you this, ls minus lh, and so it was the, where am I? ODTPME, 57. Bin, and you can see it's 191 megabytes. It's about 200 million. So 200 megabytes or so, 50,000 like that. So that's kind of so that's 4K. It's obviously looking about, so my guess is that's about a 4K buffer size, something like that. So, well, okay, I can do that. Reading this one here, some reads. It appears to be reading about 8K buffers, because the output sizes are about the same. So if we look at ls minus lh, temp, ODT, PME, like that. Yeah, it's almost identical size output and input because of binary expansion and then trimming. So that gives me an interesting idea. Right, okay, what else can I do with this one? What other nice, exciting tools have we got? Well, perf stat, let's have a look at that. Let's run perf stat on this. And this takes, as I said, about 10, 11 seconds. We will be going faster than this. We're still on version 1 of the code, just exploring the tools and seeing what's going on. Right, so this is perf stat, and it says, right, okay, 11 seconds, how much system time, etc. Clocks and CPU migrations, etc. One CPU, because it's single-threaded, running at about 2.2 gigahertz, which is about right. These numbers here are telling you what's going on the CPU. Stall front-end cycle says how long is it waiting for instructions in the decode queue, and how long is the back-end waiting. These numbers here, I wish I knew how to calculate these ones. Some of those ones you look at and go, somebody somewhere, there's a formula. Go and look at the source code and you're still not quite sure. Here. These numbers are really interesting. Right, 2.04 instructions per cycle. So this says that this particular code is running 2 instructions per cycle. It's running 2 instructions in parallel. Modern machines can do a lot more. They can do multiple ones, so Haswell's up to 6 and other ones. So it's doing superscalar, which is great. 0.14 stalled cycles per instruction, so it's waiting about 0.14 cycles for the memory. So it's pretty much running flat out on that one, so we're doing quite well there. Anyway, so that's what perf stat does. There's other bits of the perf stuff that we can have a look at. Record. So run the same thing. This is a standard profiler that just runs stuff with sampling and just gives you an idea of where things are. So if you don't want to run the slower cachegrind and get that level of X-ray vision, you don't want to have to modify anything, you can just run perf record like this and then say, right, perf report. And it goes, there you go, bingo. Right. So process, and then next thing, O-stream insert. IO write, printf. That's probably printf as well. This is output. So it appears to be spending most of its time doing writing and formatting and comparing things. These are the ones from the IO stream. And we're sort of kind of getting down into the weeds here. There's one here, I wish I knew what this one was. If somebody can tell me what this one is I'd be grateful, because it turns out to be something a bit more important later on. Anyway, you can see that it's generally smeared around. And this is what often I find when I look at an application to start off with. There's lots of things going on here. There's lots of things we can sort out. Okay, right. So what's the next thing I do? Well, let's try making it go faster because, well, so here is what I did at the next stage. So I went, there's lots of string comparison going on. So if you went back through the cachegrind, you would have seen that actually it spent a lot of time doing string comparison because it's doing, and that string comparison is because it's coming down here. It's like, well, look, if string equals string, if this equals this, I'm going, well, memcomp. I'm going to have to compare every single byte of this, every single time. Stop doing stupid things. I want to be able to say it's that thing or not. Can I just do it as an integer and just do it that? Which is exactly what I've got over here, which says, look, instead of having it as a string, I'm going to have it as an enum and a constant. That's a much better idea, isn't it? Why didn't I think of that to start with? Oh. So that's what this does. It says, right, okay, when I'm reading the things in, I go and get field type here. So when I read the thing and it says decimal, I go, right, if it's decimal, return this thing here, return 0123. So turn it on startup, read that JSON file, and turn it into binary comparison rather than a string comparison. All right, okay, so that's what that's about. Some other things that I was playing with, and I went, okay, right. And we're going, oh, look, this thing here. I'm going to the end of this is going to the end of the string, trying to work backwards to find the first non-space or null character, and then doing the translation and going, I'm going to be smart here. I can do this in a single pass. I can go forward and remember the last place. So I can do it forward like this and do that. So that's an obvious advantage, isn't it? Right, okay. And then I got a bit of sort of kind of guilt about overflow and stuff, so I put some SN printfs in there and whatever. And so you can see the type change from string to that, and that was most of that. Okay, right. So let's go to here. So let's try the same thing, and now let's try this. So this is the version 2 version, and we'll find out, hey, right, I'm twice as fast. Stop doing stupid things, yeah? Right, okay, so now I start going, yeah, I wasn't expecting it either, you're correct. It was like, oh, that was a bit of a win. So let's try recording that and then doing some, and finding out what that changed. Well, okay, so it actually changed a few things. You notice it's not doing quite so much in the way of writing now, and some of the stuff to do with that. Well, okay, we still got some other things. We're now gone up 21%. We're about 16% actually in my code rather than library code. Printf and division. I'm going, okay, right. So I had a little bit of a play around that one. I could go through all the cache results as well, but let's see what we do here if we go to this. So what was the next thing? So I'm going to, rather than going through laboriously, I'm going to go a little bit faster and just show you some of the changes. And I went, okay, right. So I went, look. All that code that I had that was doing the stuff before down here, that was doing all these things with decimals, etc., like this, which is this translation code here. I can be sneaking. I can do that with a lookup table. because I can take those two, I can take that byte there, these two things like this, and split it up into the right values and do that translation once. I don't need to do it every time, because that's good. And I also, by looking around here, I discovered that most of the time, actually, I wasn't needing to have decimal places, because a lot of these decimals were actually had .00 after them, and they're not being printed. So I could actually work out. I didn't need to use this this printf thing here, which is the, by the way, this is the printf thing. It says the number of places to print is known runtime, and I pass that in there, do that one here. So I didn't need to do this runtime one. I could do this one, hard code this one here, and hard code in the divisions. So I could get rid of some of that. Okay, that was that made me feel a little bit better. I also went, you know what? Why am I doing this thing here with piping it out? This output thing here. So I went, oh, okay, I'm going to turn it from a 3-argument to a 4-argument version and specify the output on the command line, and then redirect standard output. So use ref open. So there are a few things went on in parallel there. Let's see what we did there. Right, okay, the other thing about this one was I was using string there, and this was returning a string. So I was building up strings here. If you notice, this one is returning an integer because it's actually writing it out. This is doing much more traditional. I've got a buffer here, yeah, star, pointer, plus, plus. Yes, C programmers, you'll feel right at home with that rather than the sort of kind of string-based stuff. Okay, so that was 3. Let's have a look at 3. Right. Let's try, let's try going to there. And she was 19, yes. So we run, oops. The reason that one's there, because now it should have that. It's slightly better. Oh, twice as fast again. So all that string handling was costing me. So instead of doing strings by using just raw buffers and pointers and things, I've gained another factor of 2. So we're already, what, 4 plus, about 4 times faster than we were. Okay. Should we have another look? Should we try to see what's perf record on? We haven't run perf stat for a while. What's going on here? Let's see where we are with that. And it goes 2.25 instructions per cycle. Jason McGuinness, his comment was that most programs he sees are about 0.7 instructions per cycle. And that if you're over that, you're doing quite well. So I was already feeling quite good about this, and my branch misses are down, and I said, so we're doing really quite well here. So that's that. So it was kind of occasionally pat on the back time, but don't worry, I'll fall off that peg quite quickly. So there's, you can do perf annotate directly like this, and that will take you into there, or we can do perf record. So perf record, oops. No, not perf record, report. You can actually record things like the kernel stuff, but I'm using it in user space. I wiped out my own So that says report. Okay, now we're getting better about this. When we say a process here, we're starting to do that. You can see 30%, and I've still got some printf going on, but what I haven't done is, actually, let's go in here. So you can go into that and say, let's have a look at this thread. And it now starts to give you kind of line at a time stuff and shows, here are the hot instructions. And you can now tab your way through that and going, okay, I've got some line numbers there, so I've got some stuff like that. I can turn on line numbers if I wanted, and that tells me, right, okay, this one here, blah, 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 this is my translation, this is where it's going, here's where the speed is, if out, space, blah, 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 for whatever. So I'm going, okay, 13% here and here. So this is where all the action is. This is as a proportion of this thing here. So there are some tools you can do here, and you can say in terms of whether it's proportional to the local or global. So you've got this sort of kind of that's 4% of the total thing here, but that's 13% of this particular line on the previous one. So you can find out roughly where you're going. I've unfortunately not found a way of giving it me the Intel mnemonics, which I'd prefer, but doesn't matter. Anyway, so that's where I'm spending my time. Okay, let's see what else that. I'm not going to. That's about the only piece of my code. You can see A dot out, 30%, and everything else. Right. So at this point, I'm going, okay, I'm starting to see what's going on. And so I will have, that was 3, wasn't it? Right, okay. So I'm going to take, what I'm going to do is take that piece of code there, the get string thing, and I'm going to go over to good old Compiler Explorer, because it's just not a C++ conference without it, is it? So this is the get string thing where that loop is. That's the loop that we were doing here. So what's it actually translating into? So let's over here, 03 March native, let's have a look. So the nice thing about this one is you right click on here and say scroll to assembly, it goes, oh, that's there. So you can see as you move over these guys, what's happening on that side. So this loop, so we now got this loop here. This is the loop itself. That's this, with the if statement inside it. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8 instructions plus the loop. Notice this. This is a conditional move instruction. That is how it is coded this. So there's no branch. So it's using branch-free code at that point, which is kind of nice. So it compares that to the spec, and then we'll do an increment based on the comparison on the flag there. So that's 8 instructions. And then I had one of those kind of, why am I doing this? Why am I putting extra instructions in here when I don't really kind of need to do that? So that's one of the things. I started to feel a little bit interesting. So let's have a look at what we had here. Let's have a look at what I did next. So, right. So nothing much happening at the top here. It was all kind of the same. It's like I'm stuck in here now. There's a bit of chunk of code going on here. And I went, all right, okay. Does anybody see the completely stupid thing that I was doing here? What is just like the dope moment about all this code? It took me a while to work out what was going on. It was like, why am I doing this? Well, how is this data stored? I'm taking BCD data, turning it into binary, and then what am I doing? I'm turning it back into ASCII. I've got nibbles already split up. And what am I doing? I'm taking it, jumbling up into a nice number, and then spending all my time doing divisions and remainders trying to turn it back again. Dope! You idiot. It's already separated. All I need to do is to pull out the nibbles and just move them apart, which is what that does. So this piece of code here goes, yeah, well, actually, look, I don't need any of that. Oh, let's see if I can move it slightly. I just need to go and shift it and add in the 0 and shift this one and mask it and then add that one in and go around and do that, yes? That's just a much nicer, simpler, easier way of doing it. I don't need this lookup table. I don't need now to do anything here. There's no printf. Because you remember when I did this one, it was in div-rem and lots of other things. It was doing modulus and other. That's all just unnecessary. It's like one of those, what are you doing moments. And now I have to sort of kind of do bits of printf here myself. So basically that's the loop that does this one here. I then have to deal with the sign. So this is the D versus the C thing. I then have to work out, I have to knock off the zeros at the beginning because they gave me these decimals were padded, so I have to go and get rid of that and find the first one that isn't there, and then put a dot in maybe, because a lot of these weren't, and then I just copy it out to the output. Okay, that was a good start. So let's try that. So where does that get me? It was one of those, why are you doing this one? Why are you wasting so much time? So that should be running there. Bang, 1.79 seconds. That's getting better. Perf record. 56% in my code now. And you'll notice here that most of the stuff, so the rest of this, all that sort of kind of printf-related mods and everything else are just gone. One of the things is that when you look at things like this, it's not just a question of, oh, there's the top thing, I'll just go and bury into that. It's also looking and going, what am I doing? Why is it doing that one? And standing back and going, why is this doing lots of string comparison? Why is this doing lots of division? Why is this doing modulus? Why is this doing this stuff here? So, well, okay, I'm doing I/O like that. Okay, well, maybe, do I really need this? So there is a moment where you actually, these tools require you, or you need to stand back and reflect on what it's telling you. It's not just a big, I'll take the top thing and beat on it. It's what else is there? Which is why I'd like to know what this thing is. This second one here is, I think is like the VDSO or whatever. It's trying to get into bits of Linux. I think that's what it is.
I think the VDSO is actually in the kernel. I'm not quite sure.
Okay.
It's probably the kernel.
Okay. Thank you. And now when I do that one here, by the way, if you do, if you just go to perf annotate, you skip all that stuff and go straight to here, which is fine. Yeah, we've still got, so we're still in the translation mode here, so it's still doing the stuff. I've still got this if statement here. I'm going, do I need to do this one? Look, this compare. Why am I doing this every time round here? That's 7.5% of this one here, and that one there. This is, maybe I can do better. Anyway, we're still already in a good place, so we haven't finished yet. There's a few more versions to go. Right. Okay. So don't need that byte. Don't need that anymore. Get rid of that. We're not doing that translation because that was a bit of a failure. There were a few other things. I went, well, okay. If the field counter is not here, do the separator. So I was putting out the pipe separator every time, doing this one here, pipe separator with all this stuff. I'm doing if inside a for loop. Ifs inside for loops, can I get that one out? Yes, I can, because now I just go, well, I'll put this one here, and no, that's the next one. Anyway, so I've got something similar here. I'm just not bothering putting the null on there, but I've got a switch statement here. Maybe a switch statement's better. Let's see whether it generates better code rather than sequential tests. Well, maybe that's one thing to have a look at. So we tried a few things here. Then I went, well, okay, that was this one here. And I went, okay, so I need to do the negative thing here like this. And so I've got some other stuff. I had a slightly better way of doing this one here. And yeah, I was tweaking on the decimals there from the looks of it. That's, now, if I wasn't pushed for time when I did this, I would have taken that JSON header file, put it into a separate one, compiled it, and gone then compiled it once inside there, and had a very simple binary call across rather than have to do lots of stuff instead. But the client was not a C++ house, and I therefore wanted to give them, here's a CPP file, here's a .h file, stick them in Visual Studio, and compile. That caused me bits of fun. Some of you may have noticed that I'd forgotten to put binary on reading my inputs, and Windows has that unfortunate habit of taking Control-Z or as end of file, which is really annoying. Anyway, so that would appear to be faster. So 1.8 down to 1.2. So that one seemed to work on the. That was an improvement on the binary algorithm. So let's have a look at. So let's record that and see what it does. Port 63% in my code now. We're doing quite well. So now we're in that loop. We're still in that loop. And now we're still seeing this. You're going, yeah, I'm starting to get this nagging feeling about this. I'm going, look, yeah, I understand that translation. That's fine. But this seems to be giving me something I'm not quite so happy with. Maybe I'm doing that one. I'm going, why am I doing an if statement inside a for loop? Okay. Well, let's see what else we have then. What was my next trick? So next trick was going, if statements in for loops. Why am I doing this if statement every time inside this for loop? Yeah, I know it's not kind of big, but actually this is, given the number of fields and other things, this is doing some stuff here. Why don't I just print it out every time, and then at the end just, so print it out, comma, and the field, so separator, field, separator, field, and then just print out, then just bump one past the beginning. Hey, it's kind of hacky, but yes, hacking works in this case. And I got tests, so I was happy enough that it worked. And then I went, this if statement here, I'm really not happy with this one here. This is me trying to be smart and do single pass input. And actually turns out that it's not that good to do. So I went back to the translation loop and so translate on the way forward and then come backwards. Because I measured this one, I looked at the difference and went, okay, let's try that then. And I think that was most of that one here. And this was just a refactoring on names because outputter and temp buffer weren't very good at that point. So rank of G++. Recall time. 1.2, 1.05, okay. We're starting to do quite well here. So I'm feeling better about this. Having stopped doing stupid things, I started trying to find better things to do. 16, yeah, okay, we're still there. This kind of stuff. That sort of kind of looks fairly dense. Yeah, okay, we've got some stuff going on here. This is basically, this loop says, all right, I'm going doing that one, I'm crunching around here. And I'm looking at that, I'm going, okay, yeah, I've got some of this one here. What I'm not going to do here, just because of time, is I probably go back into the cachegrind one and going, how much am I actually spending doing this? Because this gives you some numbers. It says this amount of stuff, but how does that relate back to the application? So if you run cachegrind on this, you can go through and go, well, actually, that's, remember, I went and said while begin not equals end. You could see that these are basically the strings are mostly 4 long. That will come back at some point. We've now got a different version. We've now got this one here that had all that extra stuff in it. So let's go and have a look at the difference between that one and this. So let's go back to Compiler Explorer, and let's go and look at this second version of string. So that was the version we had before with the if statement inside, and you go, well, okay, what does that look like? It goes here, 8 instructions. What does this one look like? So let's go to here. 6 instructions. It's the hot loop. Every instruction in there costs. We've just got ourselves another 10% or more speed up. That's the kind of thing you're doing. Yes, there is another loop after this one, but it turns out that our loop doesn't run very often because quite often the number of trims isn't necessary in that case. So anyway, whatever you do, you choose to measure it, and you go, that was a good start. Right. So what's next? And I sort of had a bit of a think, and I looked at this and I went, yeah, I've been bashing on this. What about this guy? There's got to be something I can do here. I've sort of kind of, yeah, I'm kind of not kind of run out of ideas there, but I've got down to a 6 instruction loop, and it's pretty hot, and it's doing the right things. Okay, well, maybe I can do something here. And I was thinking, right. I've got nice big input, and one of my favorite tricks is the following, which is I very, 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 very much like memory map files. And I've got this big flat input. Let's go here. Right, so I boost I/O streams, memory map file. Okay, what does that look like? So here, instead of having input file, binary, need that on Windows. Damn. Works on Linux, but doesn't work on Windows with that. I map the input file here. What does that do? It says, well, I have this 200 megabyte file. What I want to do is just to stick it straight into my address space and then give me a pointer, in this case, const data. So what does this do? I'm going to say, right, So I'm going to change this to say, yes, my output file is there, but the input file is a const char pointer and a size. It's 200 megabytes, there you go, big array. I don't need to read it in anymore. I don't have to do any of that read and write stuff there. Well, I don't have to do the read stuff, sorry. I still have to do the write. So I go through and I go, right, okay, so I just made some changes here, and so I've just changed that around, and I've now got some stuff about taking the pointer, and instead of saying is the buffer, it's the input file directly, so I'm not actually copying the data from the file in through the operating system on the C runtime library and whatever into this one. I'm going, it's there, and letting the operating system do it. Stick a new line on the end. By the way, do not use endl for performance. So if you see out with endl, because endl does new line and flush. So those of you who don't know that one, endl can slow your code down a lot. But I am choosing to still do output through the standard streams. Okay, so let's have a look at that one. It's basically kind of something very similar. I just need to make all that lot work with slightly different input. Okay. Yes, that will now horribly not link, thank you. Have you seen my talk before? I'm glad somebody's watching. That didn't link because I now need to link. So boost IO streams is not a header-only library. There is something that has to go with it. So now let's see what that looks like. Bang. So what do we have before? 1.057 and 2. Okay, so I'm knocked 0.1 second off, so I'm 10% faster. And interestingly enough, also the user time's gone down, as well as the system time. So the system time is a quarter of what it was. Sorry, it's knocked off a quarter. Let's have a look. Record. So what's happening here? Where's it going now? This becomes mildly addictive, as you may have noticed. Right, 70% in my code now. Yay, and I've got some other stuff here, but all these stuff is done at the 4% level. So it's basically my code and the operating system from the looks of it. So 70, 80+% online. Right, what we haven't done for a while, and now I've changed that, is to say, let's go and have a look at that. Let's try an strace on this. Now, what do I see? Right. There's no read. These read calls here aren't really the recalls there for other things. The operating system is doing it all for me. As far as strace is concerned, it's going, yeah, that's fine, it's just there. I mapped it in, I don't need to do anything. That's pretty nice. So it basically seems to have cut out a whole pile of stuff. Instead of my application reading from the buffers, from the streams, which is reading from the operating system cache, I've just gone straight there. Can I have that, please? And you just page it in. And because I'm going linearly like that, the operating system can work that out and go, yeah, I'll have that, thank you. So it saves a considerable amount of time. Anyway, 25% off my CPU time there. So I was feeling quite good about this at this point. And so I thought, okay, I can do better than this, can't I? Right, so what do I do at this point? I went, okay, I've got my memory map file, and at this point I'm now going to do some stuff and going, this is a 6-byte loop. I'm doing a character at a time, because I can use a 256-byte lookup table. And then I went, maybe I can do 2 bytes at a time. But then I go, 2 bytes at a time is now 64,000 elements, but it's 128 kilobyte lookup table. 128 kilobytes, that's bigger than L1. It's kind of filling up L2. Is this going to be faster or not? So I thought, I'm going to try a 2 byte at a time translation table. So instead of translating one byte at a time, episodic dash-again, pick up 2 characters, look into a bigger thing and say, right, I'm going to translate this one, output here. So what do I need to do here? I need to deal with the 1 byte offset. So if it is offset, I went, well, also, what do I do about alignment and other things in here? Because does that work on an Intel chip well enough? It doesn't work on old things like MIPS and whatever, but I go, I'm going to try it. Maybe yes, maybe no. So we do this one here. We go, right, okay, I've now got a translation. So translate and translate 2. And this is length divided by 2. So this is now my output 2. And I've put a pointer here and alias this unsigned short to that. Yes, it's horrible hacking. You saw it here first. And here is the unsigned short lookup table. 256 by 256, so it's 64K entries. And that unsigned short, 16 bits. Okay. Anybody got any, do we think that's going to be faster or not? That's the question. Ooh. Anyway, I thought, well, I'm going to have to try, aren't I? I'm going to have to. So let's try, and oh, yes. Yes, we're somewhat faster than we were. So that's at 0.82, and that was 0.9, so I'm another 10% faster on that. That seemed to work on this particular data set. Okay, right, well, I could go over here and go, well, we could do this and go, yes, let's have a look at this. And you go, well, what does that look like in the wonderful world of Compiler Explorer? Well, it looks like this. And you go, what does this translation one look like here? So you go, yep, so this is you can see here that this has got a loop. So this is where's that loop? That loop should be up here. No, it's not a loop, sorry, because it's an if statement. So you can see it does a byte translation next late here, and this one is doing the loop on translate 2. Okay, so it's basically exactly the same loop that we had before. It just says word rather than byte. So that's what that gives you. And so I was happy enough that that A, went faster, B, wasn't doing anything particularly horrible. Of course, now I went, well, there's always got to be more here, because I think I can have some fun. Because I went through and I went, you know what? Most of my things are all, I know the sizes of these strings, so I can use domain knowledge. I know that, and I've looked through, well, they're 1s or 2s or 4s or 8s. I haven't got any 7s. So why am I got this loop that can handle any size when actually most of the time, maybe I can special case these ones. So I went, okay. So I started to produce these. So I had some templates like this, and I've got a template that says, yeah, okay, this is just the 1 byte version because it can handle it directly. Translate these ones here for n, and I've got a specialization that says, if you give me -1, whatever, this will do this one here. Otherwise I can, because the point about this, these look the same. You're going, why? This length here is a runtime length. This is a compile time thing, and what happens, you'll find that the compiler goes, oh, I know how big that is. I can unroll it. Ah, that was the theory. Okay, let's have a go. So I thought, well, I'll take all that kind of get string stuff, because that's where all the action was, and I'll have this switch statement like this. And I'm going to do a switch for 1, 2, 4, 8, and anything else, it will use the, so you can see here it says translate 1, 2, 4, 8, and -1 for anything else, and that will take the length here. Otherwise, it takes this one here. I borrowed that, this sort of trick from various people. I think Arnaud de Citiel pointed me at in that direction. Well, let's see what happens there. What do you think, guys? It's a cliffhanger, this one, isn't it? Yeah, it's like, oh, okay, right, okay. That's slower. Okay. Now, let's see what happens if I... I tried this one and found that that was actually slower, and I went, well, okay. If I do things like this, for instance, I found that actually the interesting thing is that it depends how many you have here. So it starts becoming critical on the way that GCC has implemented switch statements. So I'm going, well, let's see what that looks like. And I go, that's faster. So I comment out one of the switch statements and it goes faster. Okay, right, fair enough. So I'm now at that point, and you've sort of kind of got to the top, and then the things you start trying, you find that actually you just make it worse. So you have to be a little bit careful about these ones here, and there's sort of almost a limit that you get to of that. We're almost there in terms of limit, but there's probably... So I tried some other, there's a few other things I was trying, which is well, you know what, this is C++, and so why am I building all of this here at runtime? It's a translation table. I can build it at compile time. Yes, const_expr. So I couldn't put it directly in where I was, so I pulled it out of a separate thing. So I had one const_expr thing for the 1-byte translation, const_expr compiler. You do need to have this little piece in, by the way, because otherwise it will complain about the array, because it goes, the array is default initialized, so you need to call the constructor directly like that, so it'll be value initialized, because otherwise it goes, ooh, I've not initialized it. Yeah, because C++. Anyway, the translator was basically the same, and I just ripped out various parts of this. So here's the 2-byte translator, which is initialized directly from the 1-byte translator. You can see it calls that one. So just doubles that one, and then, so this is basically the same thing, it's just using the translator. And turns out it's actually not that much faster, because creating that table is not really measurable as part of that. Well, remember, it didn't really turn up anywhere on the profiling, so it was just one of those kind of things because I thought I should. So that was about that. I think the last one I had, that was going to be something which I haven't done, but it would be the next place I would look, which would be this, which says, well, I'm not going to bother with that translator, etc., or the const_expr, but the key point there is actually, have I got that one down here? Yes, I am comparing 9 and 11. That is intentional. Memory mapped output. Memory mapped input is simple. It's fixed size. I know how big it is. Memory mapped output is considerably harder because I go, how big is it? I don't know until I've read the input. And even then I go, well, I probably need to take some factor saying it's about the same or add 20%, create the thing, and then truncate it, which I've not gone through, but that would probably be where I would go next. So I'm going to leave that at 9 as being the fastest so far. I think that's probably about, that's 9. But there is one more trick. So I think that's probably, let's see what's going to give me. And we're now down in this sort of kind of noise. So I'm not sure. That's like 1.5% slower. Maybe if I run it again, I'll get another number. I don't know. Okay, so let's try it without the unrolling the loops. Maybe it's faster, maybe it's not. Okay, so it's actually unrolling those loops doesn't make it go faster. Anyway, so that's sort of kind of pretty much there where I got that one. This was just some of the tools I've used: valgrind, cachegrind, perf, compiler explorer. I didn't use any of these ones here, but we did look at strace. We looked at how much that the memory mapping makes a difference in there. That was just emergency non-internet version. Start with a simple application. And avoid gross inefficiencies, and do a lot of measurement, use a lot of tools, and simplicity is your friend. You'll notice you start off with simple code, you go through more complex code, and when you end up really going fast, you end up with simple code again, because you can only go fast if you actually have really simple code. Right, that's it.